Okay. Good morning, everyone. We are recording now. All right. So, are there any questions or concerns regarding anything we discussed yesterday? Right. So, one of our main goals is to prove that the feasible region of any linear program is a convex set, which is the same as saying that all polyhedra are convex sets. And we noted that we just need to do two things, and that would be a very natural way to prove the statement. First, we would prove that all half spaces are convex. And second, we would prove that the intersection of any number of convex sets is another convex set. And that is sufficient to prove what we want to prove. And we, in fact, proved the second one. We proved it for two convex sets, and I gave it as a do-it-yourself exercise to prove it for any number of convex sets. The same argument, basically. And now what remains to prove is that all half spaces are convex. Okay. So I asked you to try it on your own. Did anybody prove it on their own? Did anyone try to prove this? That the convex combination of x prime and x double prime also belongs to the same half space.
So there wasn't much to prove for this. Like it should
Exactly.
have been like a single sentence. It wouldn't have been much of a proof.
Exactly, right? So that let's just write it down for the sake of completeness, right? So we are taking a convex combination of, so this is our x bar, and we need to show that x bar satisfies the inequality, where x bar is a convex combination of the two given points, right? So let's just make sure we are, sorry, I think I wrote alpha, I meant to write A transpose. Okay, so A transpose x bar is simply A transpose times lambda x prime plus 1 minus lambda x double prime, right? And by standard vector multiplication rules, you get this, right? And our goal is to show that this is less than equal to beta. So can anyone tell me what happens at this point? How do I get to the final conclusion that it is at most beta?
A transpose x bar is less than, it should be less than beta because that point is in the plane.
A transpose x prime is less than equal to beta, that I agree.
Less than or equal to beta, and even A transpose x double prime is also less than or equal to beta.
All right. Okay, this is fine. All right. And what else do I need?
I think this should be sufficient. I mean, this shows that this whole thing will be less than or equal to beta.
Is that clear? What if lambda is 5?
Oh, okay. Oh, but lambda is always between 0 and 1.
Exactly.
I mean,
so you're using that point, right? So this is not sufficient. You are using the fact that lambda and 1 minus lambda are both between 0 and 1. Both of these quantities belong to the interval 0, 1, right? And that implies that this is less than equal to beta plus, lambda times beta plus 1 minus lambda times beta, right? And that is exactly equal to what we want. Okay, so we are using a few things as we would expect to, and that is our proof. So this implies that x bar indeed satisfies the linear inequality we care about, right? And therefore it belongs to the half space. So we have shown that for any 2 points in the half space, any convex combination belongs to the half space, and that completes our proof. Okay, so half spaces are indeed convex. Are there any questions or concerns regarding any of this discussion? In fact, probably I should not say lambda belongs to the open interval. I can very well say it belongs to the closed interval. Yeah. The arguments still go through, and we are looking at all convex combinations. Okay. All right. So that proves that the feasible region for any linear program is a convex set. It could be infeasible, in which case it is the empty set, which is also convex. Okay. All right. So next I
Sir,
want to,
I
yeah,
did
go
not
ahead.
understand that fact. How is empty set convex?
Why not?
I
For
mean,
any 2
there is no
points,
element.
that's
Oh,
okay.
okay. Is it a
For,
vacuous
yeah,
truth?
it is vacuous truth, right? For
Okay.
any 2 points, the convex combination belongs to the same set.
Okay, because there are no points, it's just a vacuous truth. Okay.
Exactly, exactly, right. All right. So, so in that case, I would like to continue the discussion on convexity, but I would like to focus on extreme points now, right? We have already looked at extreme points. That is how we started our discussion yesterday. So let's write down things a bit more rigorously, and let's focus on extreme points for the rest of today. All right. So all right, so maybe I'll put down the exact explanation I wanted to convey yesterday. So a point X is properly contained in a line segment L, right? So we can assume that we are working in Rn for some n, okay? If X is a point in the line segment, however, it is not one of the 2 ends of the line segment, but X is not an end of the line segment. So, given a convex set S in Rn, a point is an extreme point if no line segment that properly contains X is a subset of the set. Right? In other words, if L is a line segment that properly contains the point X, then L cannot be a subset of your set. Okay, so this is precisely what I was trying to convey, but I think I did not have the necessary terms for it. So if you look at a cube in 3D, okay, my drawings are not great, but anyways, that, okay. This should also be a dotted line. All right. So if you look at a cube in 3D, the extreme points are exactly those points for which you cannot draw any line segment that properly contains the point and is contained in your set. Okay. And another way to think about it, which is exactly equivalent to this definition that I would like you to convince yourself, is it's the same as saying that the extreme points are precisely those points that cannot be expressed as a convex combination, as a proper convex combination of two distinct points in the same set, right? Supposing you can draw such a line segment, which is given here, a line segment that contains x and is contained in the set, then you can write the point as a convex combination of the two ends of that line segment. Okay, so these two statements are the same. So I want to write down this as well. This is 2.19 GKT. It's simply a definition that is equivalent to what we have written above. Okay, and it says that a point in a set, convex set, is not extreme, not an extreme point, if and only if you can write it as a proper convex combination of two other points. Okay, so does everybody see why these are all equivalent statements? We haven't said anything deep so far, right? We have just written down the definition in a bunch of different ways. Okay. All right, so all of this is fine. Let me ask you the following question, very standard question that I like to ask. How would you convince someone that a point is not an extreme point?
Find the line segment which is a subset of S, for which this point is properly contained in it.
Right. Or in other words, you just write it as a proper convex combination of two distinct points, right? Which is the same as what you said. Right? So if you find those 2 points, x prime and x double prime, the endpoints of the line segment you propose, then you are done, right? What about the converse? How would you convince someone that a point is indeed an extreme point?
So we need to take every 2 points in that region and show that, okay, this is not a proper linear combination.
Convex combination.
Convex combination.
Right. Exactly. Right. So this is not so straightforward, right? You don't want to do this for every 2 points because first of all, there are infinitely many points. Right. So it's not immediately clear how you would do this. So that is one of the motivations for the next discussion. So we are going to take a look at extreme points. So this is a very geometric way of looking at extreme points, what we have discussed so far. Okay. But yesterday when I was asking, someone also gave a more algebraic way of looking at it. I don't know who it was. But if you go to a 2D example, maybe let me just draw it here. If you consider one of our 2D examples, let's say I consider x1 plus 2, sorry, I think it was 2x1 plus x2 less than equal to 9, x1 plus x2 less than equal to 7, minus x1 plus x2 less than equal to 5, and x1 is at least 0. Okay. For the rest of this discussion, I'm going to write down all constraints as less than equal to. So I'm going to multiply the last constraint by -1 and put it as minus x1 is less than equal to 0, right? Which is the same as what was written earlier. So if you look at these 4 constraints, these are the 4 constraints of LP2 that we were discussing earlier. LP2 constraints. I don't want to look at the objective function, so let's not care about it. So what do you get? Well, I'll make a weight drawing here. So the first line looks a bit like this, 4.5 and 9 are connected. The second line looks a bit like this. And the last one looks like this. In fact, my drawing is, yeah, let me. Okay. And these 3 points that you can see here, those are your points that are the extreme points for this particular polyhedron. Notice that the feasible region is everything here. It is not a polytope, it is a polyhedron. And these 3 points that you see here are 0, 5, 1, 6, and 2, 5. Okay. So someone mentioned that these 3 extreme points, they are the intersection of 2 lines in this drawing. Every point is the intersection of 2 lines, 2 of the hyperplanes that we have drawn. If you go to a cube, then each extreme point is the intersection of 3 hyperplanes. Hyperplanes in R3 are going to be 2-dimensional objects, right? So they're going to be basically planes as you think about them, right? In R2, hyperplanes are simply lines. And so every extreme point is the intersection of 2 distinct lines at that unique point. The extreme point is that unique intersection, right? In this case, every extreme point is the unique intersection of 3 different planes. Okay. The number of planes is the number of sides in a cube, which is equal to 6. Okay. So it turns out that is not a coincidence. There is a very algebraic way of thinking about extreme points that is equivalent to the geometric definition that we have discussed. Okay. And that is exactly what I want to discuss next, and we will prove it. We will prove that this geometric definition is exactly equivalent to an algebraic characterization of extreme points. Okay. Are there any questions or concerns regarding where we are heading? Okay. So I would like to write down this these constraints in a matrix vector format. Okay. So we are going to have 2, 1, 1, 1, minus 1, 1, and minus 1, 0. This is our matrix A. We have the column vector of variables x, right? I'll just write it down for the sake of completeness. Sorry, my bad. It's just 2 variables. And we want this to be less than equal to the right hand side, which is our vector B, 9, 7, 5, 0. Okay. So in general, we have some polyhedron expressed as ax less than equal to b. All the constraints can be captured in this format. Right. Okay. And this is our first constraint. This is our second constraint, third and fourth. Each row corresponds to 1 constraint. Each column corresponds to 1 variable. Okay. And what I want to do is I want to look at these three extreme points and I want to understand what's going on with them. 0, 5, 1, 6, and 2, 5. Okay, so these are our three extreme points. So what we are going to do is, given any point, we are going to look at the constraints which hold with equality and the constraints that do not hold with equality. Okay, just to give you an example, for 0, 5, if you plug it into these constraints, right? Can anyone tell me which of the constraints hold with equality? There are 4 constraints, 1, 2, 3, and 4.
Third and fourth.
Third and fourth, exactly. So we are going to call these as the tight constraints with respect to this point. So the tight constraints of 0, 5 are going to be third and the fourth one. Okay, I'm just using this notation. What I mean is the tight constraints. And the other constraints, we are going to call them the slack constraints. Okay, there is some slack over there. So the slack constraints for 0, 5 are the first and the second ones. Okay. Similarly, for 1 and 6, let's see what the tight constraints are. Clearly not the first one, because it's 2 plus 6, 8 less than 9. 1 and 6, 1 plus 6 equal to 7. So the second one, minus 1 plus 6, 5. So the third one, and the fourth one is not tight because it would be minus 1 less than 0. So the tight constraints are 2 and 3. And the slack ones are 1 and 4. Okay. And look at the last one. A geometric way of looking at it is to see which of the two lines are meeting there, right? So that would be another way to figure out which constraints are tight. So it's the second line, x1 plus x2 equal to 7. And it is also the first line, 2x1 plus x2 equal to 9. So the first and the second are the tight constraints, and the other two are slack. Tight of 2, 5 is 1 and 2, and the other two are slack constraints. Okay. And what's going on here is that whenever you have an extreme point in this two-dimensional example, you have two lines meeting at a unique point, right? That means that the linear equations corresponding to those two lines, they have a unique solution, which is where your extreme point is, right? So you can see where we are heading. We are heading towards the rank of the matrix. Okay, so what we want to look at, we want to look at the matrix corresponding to the tight constraints. Okay, so we are going to call it for a extreme point x bar. We are going to use the notation A tight of x bar, and that will just capture the tight constraints. We will not look at the other constraints, right? So for example, A tight of 1, 6, the tight constraints are the second and the third one. And so what we get is the second and the third rows of the matrix. We get 1, 1, minus 1, 1. Okay. And we are going to use a similar notation for the right hand side vector. B tight of 1, 6 is going to be exactly those two entries of the B vector, 7, 5. Okay. Can anybody tell me what A tight of 2, 5 is? 2, 5 is the point where the
2,
tight
1, 1, 1.
constraints. Yeah, exactly. 2, 1, 1, 1, right? It's the first two rows because those are the tight constraints, 1 and 2, right? And similarly, B tight of 2, 5 is 9 and 7. Okay, so this is just notation so that life is a bit simpler. In the text, they use A equal to, which would be easier to write, but I think it's a bit more confusing because we will have equal to's floating around and we will have two different ways of looking at equal to. So I won't be using that. I'll just write down A tight. Okay. Good. All right. Okay. So what do you think should happen? If a point is extreme, what do you think the A tight matrix, what should its rank be? Supposing A is an m by n matrix, right? So you have m rows and n columns, and B is going to be an m by 1 vector, right? Okay, and x, of course, yeah, get it? X is 1 by n. Sorry, I think I made a mistake. N by 1. Okay. So if A is an m by m cross n matrix and B is an n cross 1 vector, what do you think should the extreme points A tight matrix, what should the rank of that matrix be? We want the linear
Full rank.
equation. Sorry?
Full rank. So all n.
Full rank.
Then
Exactly. It should be equal to n, right? So already by this discussion, you can see that the rank of the matrix should be equal to n if the point is an extreme point. And that is exactly what we'll be proving. So this is 2.20 GKT. So let's say P is our polytope, which is all the points x that satisfy ax less than equal to b. And the claim is that any point x bar of this polytope is an extreme point of our sorry, I should write polyhedron, my bad. It's an extreme point of the polyhedron if and only if the rank of the matrix corresponding to the tight constraints is exactly equal to n, right? Where A is m cross n. I think the dimension of the rest just follow from A's dimension. Okay. So let's look at an example which is not an extreme point. Can somebody give me a point that is on one of the lines but is not an extreme point? Right, we have
3, 3.
3, 3. Is it on one of the lines though?
Yes, sir. I think it was on 1. Yeah,
Right,
it was
right,
on
right.
1.
Right, 6 plus 3 equal to 9. Thanks. Good. So 3, 3 is indeed on one of the lines. It should be on line 1. So it should be somewhere like here, right? Somewhere here. Yeah, that would be somewhere like 3, 3. Right? So if you look at 3, 3, let's say if that was your x bar, then the A tight corresponding to x bar, the only constraint that is tight is the first constraint, right? 6 plus 3 equal to 9. All the other constraints are slack constraints, right? And so your matrix would just have one row, the first row, right? And that is clearly not a full rank matrix. Okay. So is everybody happy with this statement? Is the notation and everything very clear? Are there any concerns regarding what the statement is saying? Okay. So let's prove this. I don't think we'll finish the proof today, but we'll prove one direction. That should be fine. Okay. So let's suppose we are proving the converse direction. Okay. So let's say the rank of this matrix is exactly equal to n. Right? And our goal is to show that this is an extreme point. Okay, which means that we cannot write it as a proper convex combination of two distinct points. But let's suppose that we could write it as a convex combination of 2 points, and then we will try to prove that the 2 points have to be the same, so they are not distinct. In fact, they will be the same as the given point. Okay, so let's suppose that the given point x bar is a convex combination of 2 points okay, and we will show that both of these points are the same. Therefore, it cannot be the convex combination of two distinct points. Okay. So how shall we proceed now? Remember, what we know is that this matrix has rank n, right? So, well, we don't have that much information here. We just know the linear inequalities. So how about we look at the linear inequalities for this particular point with respect to the tight matrix and see if we can make some progress there. So let's say we look at A tight of x bar, and multiplied with by x bar. Okay, so we are taking just the tight constraints rows and looking at what happens there. So, well, what is this? This is, we look at the tight constraints and we expand this into lambda x prime plus 1 minus lambda x double prime. Right? Which, as we did before, is lambda times A tight x bar times x prime plus 1 minus lambda times A tight x bar x double prime. Okay, we know that x prime and x double prime are actually in our polyhedron. What does that mean? how can we use this information now to write the next step? Anyone? What can you say about this with respect to this vector? Is there some relationship between them? Remember, x prime and x double prime are our feasible solutions, right? They are in the polyhedron, right? So that means that x prime and x double prime, they satisfy ax less than equal to b, which means for every component of the left hand side, it has to be less than equal to the corresponding component of the right hand side. So therefore, each component here has to be less than equal to each component here. Does everybody see that? Right? So since x prime and x double prime are feasible solutions, they are in our polyhedron, I can write down that this is less than equal to lambda times b tight x bar plus 1 minus lambda times b tight x bar. Does everybody agree with this step? Do you see why this is true? Okay, I guess there are no questions. So I'm assuming you see this is true, right? And that is what? That is exactly b tight x bar. Okay. How do we complete the proof at this point? What is this equal to? Given that we are looking at the vector x bar and we are looking at the tight constraints, what can you say about this quantity?
Equal. It was equal to b tight with x.
Exactly. This is equal to b tight x bar because we are looking at the tight constraint. So by definition, the two vectors have to be equal, right? That's the definition of the tight constraints at the vector x bar, right? But now we have a situation where this is equal to this, and therefore everything in between has to be equality, right? In particular, these two quantities have to be exactly equal. And similarly, these two have to be exactly equal, right? So just to not make it confusing, so equality holds everywhere which implies that actually in order to make that statement, I need lambda to be not 0. Because if lambda is 0, then it wouldn't matter. Actually, it doesn't matter because at least one of lambda and 1 minus lambda is not 0. So at least for one of the 2 points, I can say that equality holds. Okay, no problem. Okay. I made slight changes to the proof that was in the text. So now I have to make changes accordingly. So equality holds everywhere since both lambda and lambda 1 minus lambda cannot be 0. We have Okay, both of them cannot be 0. So either A tight x bar has to be multiplied by x prime has to be exactly equal to B tight x bar, or the same thing should hold for x double prime. So either A tight x bar times x prime equal to B tight x bar, or the same statement holds for x double prime. Okay. Now what can you say? Can you use some linear algebra to make some conclusion? You know that the rank of the matrix A tight x bar is exactly n. So what can you say about the equation? Right. So given that the rank of A tight x bar is equal to n, what can you say about A tight x bar times x equal to B tight x bar?
And there is a unique solution.
There is a unique solution, right? Right. It has a unique solution. And in fact, the unique solution is x bar, right? That was the definition of x bar, right? It is exactly the tight constraints are exactly those which are tight for x bar. So x bar satisfies all of them, right? So because of this unique solution, we conclude that either x bar is the same as x prime, or x bar is the same as x double prime. Okay. But if you are able to write a point as a convex combination of 2 points, and one of the point is itself, then all of them have to be the same points, right? Right? What does convex combination mean? It means that you're writing some point x bar as a convex combination of 2 points, right? But if one of the points is exactly the same as x bar, then both of the points have to be the same as x bar. Do you agree with that? Right? Okay. So I'll just put a y over here and let you think about it. Right? It basically goes to what does it mean to say that a point is a convex combination of 2 points. Right? It basically means that you have drawn a line segment around that point, and you have written that point as a convex combination of those two ends of the line segment. So both the ends have to be distinct from x bar. So if any one of them is the same as x bar, then all of them are actually the same. Okay, and that is exactly what we wanted to prove. We wanted to prove that x prime and x double prime are indeed the same. Right? So that proves that you actually cannot write it as a proper convex combination. So the only possibility is either for x prime and x double prime to be the same, or for lambda to be 0 or 1. Thus, x bar is indeed an extreme point. Okay. All right. So that proves the reverse direction. We still need to prove the forward direction. Okay, so it's already 9:48, so I don't think I want to get into the forward direction proof, which is a bit longer than the reverse direction. But the reasons I'm covering these proofs is because you will be writing lots of proofs on the assignments, right? So especially the coming up few assignments, some of the problems you will be expected to use linear algebraic arguments. And then when we move to module 4, we will have both a mix of algebraic and combinatorial or graph theoretical arguments. Okay. The good thing about this theorem is that you can actually convince anybody that a point is an extreme point. You just look at the type. You don't need to look at the geometric drawing yet, right? Because you may be working in n dimensions, you won't be even able to do that, right? But you can just look at the matrix corresponding to the tight constraints. You can compute the rank of that matrix, which is actually polynomial time doable, as you must know. And that is enough. That way you can convince anyone that a point is actually an extreme point. So that's one way to look at this result. And another way to think about it is that it's an algebraic characterization of extreme points as opposed to geometric. Okay, so that's all for today. We will continue this proof on Monday. We'll finish it. And then we will have a little bit of a discussion about convex hulls. You might have already seen them in your previous courses. Right? So we'll also have a brief discussion about convex hulls. And we might also talk about the convex hull of perfect matchings of a graph, which is called popularly as the perfect matching polytope of a graph. So we'll relate this to some graph theoretical concepts, in particular perfect matchings, which might be related to one of your assignment 2 problems. Okay, and then we will move on to module 3. So most likely Wednesday, we might be able to start module 3, where we will be looking at everything more algebraically, and we will be, in particular, one of the main goals in module 3 is to understand how the simplex method works. Okay, and there's going to be a lot of linear algebraic manipulations in module 3. So hopefully this gives you a little bit of a taste of the kind of linear algebraic manipulations we'll be doing. Okay. All right, so that's the end of today's lecture. But if there are any questions or concerns, I'm here for another 10 minutes.
Sir,
Yeah, go ahead.
is it possible to find another collaborator? I think I asked Harsha, but I mean,
Okay.
Harsha is busy in his own way. I
Let
mean,
me
he
stop the
told that.
recording. Yeah,
Okay,
let me
sir.
just stop the recording so that we can discuss these things.
Yes.